Let me ask you something right now. Wherever you are sitting, whatever device you are watching this on, I want you to look at the time. Look at the clock on your phone, the watch on your wrist, the little numbers in the corner of your screen. You see those numbers ticking? Seconds passing, one after another, steady, reliable, constant. That clock feels like a heartbeat of the universe, does it not? It feels like every second that passes for you passes for everyone, everywhere, at the same pace. Your friend across the street, your cousin in another country, an astronaut floating in space, a particle racing through a collider, a photon flying through the void of the cosmos. Surely, they all experience the same tick, the same tock, the same flow of time. Right, wrong, and I mean profoundly, deeply, fundamentally wrong. Not wrong in some abstract philosophical sense, not wrong in some poetic, metaphorical way, wrong in the hardest, most concrete, most experimentally verified way that science can tell you something is wrong. The clock on your wrist and the clock on a spaceship moving at high speed do not tick at the same rate. A clock near a massive object and a clock far away from it do not agree. And here is the part that will keep you up tonight. It is not because the clocks are broken. It is not because of some mechanical error, some engineering flaw, some trick of measurement. It is because time itself, the actual fabric of what we call time, passes at different rates depending on how fast you're moving and how deep you are in a gravitational field. Time is not what you think it is. Time is not universal. Time is not absolute. Time is personal. And today, we are going to go so deep into this idea that by the end of this video, you will never look at a clock the same way again. Now, before I take you on this journey, let me give you a taste of what we are dealing with here. In 1971, two physicists named Joseph Haefel and Richard Keating took 4 cesium atomic clocks, the most precise time-keeping devices available at the time, and they put them on commercial airplanes. Regular commercial flights, they flew one set of clocks eastward around the world and another set westward around the world. A third set of clocks stayed on the ground at the United States Naval Observatory. When the flying clocks came back and were compared with the ground clocks, they were different. Not by hours, not by minutes, not even by full seconds, by nanoseconds, billionths of a second. But they were different, and they were different by exactly the amounts that a man named Albert Einstein had predicted over half a century earlier. The moving clocks had run slower. Time itself had passed at a different rate for the clocks that were flying compared to the clocks that stayed still. Let that sink in. This is not theory. This is not a thought experiment. This happened. This was measured. This is real. And here is something even more immediate, even more present in your daily life. Right now, as we speak, there are satellites orbiting the Earth that make your GPS work. The global positioning system, the thing that tells your phone exactly where you are, that guides your car through unfamiliar streets, that lets delivery drivers find your house. Those satellites carry atomic clocks, and those atomic clocks are constantly being corrected for the fact that time passes at a different rate up there than it does down here. If those corrections were not applied, if we ignored what Einstein taught us, your GPS position would drift by about 10 kilometers per day. 10 kilometers? Every single day. Your GPS would become completely useless within hours. So every time you open Google Maps, every time you call a ride, every time you navigate somewhere, you are relying on the fact that moving clocks run slower and clocks in weaker gravity run faster. You are relying on time dilation. You are relying on Einstein every single day, and you did not even know it. So today, in this video, we are going to go on a complete journey through one of the most beautiful, most mind-bending, most experimentally confirmed ideas in all of physics. We are going to start from the very beginning. What is time? What did we used to think time was? How did one young patent clerk in Switzerland destroy everything we thought we knew? We are going to understand special relativity, not with complicated math, but with pure logic and simple thought experiments. We are going to see the light clock, the most elegant demonstration of time dilation ever conceived. We are going to walk through the twin paradox and resolve it completely. We are going to see real experiments, real data, real proof that time dilation is not an illusion. We are going to enter the realm of general relativity, where gravity itself bends time. We are going to visit black holes, where time nearly stops. We are going to ask what all of this means for the nature of reality, for free will, for the future of space travel, for the very meaning of existence. And I promise you, by the end of this video, your understanding of the universe will be fundamentally different from what it is right now. If you are the kind of person who gets excited about having your mind completely blown by science, if you love going deep into the mysteries of the cosmos, then you are in the right place. Hit that subscribe button right now. Turn on the notification bell and tell me in the comments where you watching this from, what country, what city. I want to see how far across this beautiful planet this video reaches. Because what we are about to discuss today does not care about borders. It does not care about languages. The laws of physics are the same everywhere for everyone. And that, as we are about to discover, is precisely where the whole story begins. Let us start with the most fundamental question we can ask. What is time? I mean, really, truly, what is it? This seems like it should have a simple answer, but it does not. Ask a physicist, and you will get one answer. Ask a philosopher, and you will get another. Ask a poet, and you will get something else entirely. We all experience time. We feel it passing. We remember the past. We anticipate the future. We live in what we call the present. But what actually is this thing we call time? For most of human history, we measured time by observing regular, repeating patterns in nature. The rising and setting of the sun gave us the day. The phases of the moon gave us the month. The cycle of seasons gave us the year. Ancient civilizations built sundials to track the sun's movement across the sky. They built water clocks, where the steady drip of water from one container to another measured intervals. They built hourglasses filled with sand, and then came mechanical clocks with pendulums, swinging back and forth with remarkable regularity. Each of these devices did the same thing. They counted repetitions of some regular process and called that the passage of time. But all of these measurements were based on an assumption, a deep, unspoken, seemingly obvious assumption. The assumption was that time itself is a thing that exists independently, that flows at a constant rate, that is the same everywhere and for everyone. The clock does not create time. The clock merely measures a pre-existing universal flow. Time is like a river, and we are all floating in it together, carried along at exactly the same pace. This is what feels true. This is what our everyday experience tells us. And for centuries, this is what the greatest minds in science believed. The person who most powerfully formalized this idea was Isaac Newton. In his masterwork, the Principia Mathematica, published in 1687, Newton wrote some of the most influential words in the history of science. He said, and I am paraphrasing here, that absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. Read that again. Time flows equably without relation to anything external. It does not depend on anything. It does not respond to anything. It just flows. Steadily, universally, absolutely. This is Newtonian time. This is the framework within which Newton built his laws of motion, his law of universal gravitation, his entire description of how the physical world works. And it worked beautifully. For over 200 years, Newtonian physics could predict the motions of planets, the trajectories of cannonballs, the orbits of moons, with extraordinary accuracy. There seemed to be no reason to question the idea of absolute time. It was obvious. It was intuitive. It was confirmed by everything we could observe. But here is the thing about the universe. The universe does not care about what is obvious to us. The universe does not care about what feels intuitive. The universe operates according to its own rules, and those rules are under no obligation to make sense to creatures who evolved to avoid predators on the African savanna. Our brains are pattern recognition machines optimized for survival, not for understanding the deep structure of spacetime. And in the late 1800s, the cracks in Newton's beautiful, intuitive picture of absolute time started to appear. The trouble started with light, specifically with the work of a Scottish physicist named James Clerk Maxwell. In the 1860s, Maxwell unified electricity and magnetism into a single framework, what we now call Maxwell's equations of electromagnetism. These four elegant equations described how electric and magnetic fields interact, how they give rise to each other, how they propagate through space, and buried within those equations was a constant, a speed. The speed at which electromagnetic waves travel through a vacuum. Maxwell calculated this speed from purely electrical and magnetic measurements, and the number he got was approximately 299,792 kilometers per second. This was, within experimental error, exactly the speed of light. Maxwell realized that light itself was an electromagnetic wave. This was a monumental discovery, but it raised a deeply troubling question. When Maxwell's equations gave the speed of light, they gave it as a bare constant. They did not say the speed of light relative to the Earth, or the speed of light relative to some observer, or the speed of light relative to anything at all. They just said the speed of light is c. But in Newtonian physics, speeds are always relative. If you are on a train going 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone standing on the platform sees the ball going at 150 kilometers per hour. Speed depends on your frame of reference. So the speed of light relative to what? Scientists in the 19th century assumed there must be some medium, some substance, through which light waves propagated, just as sound waves propagate through air. They called this hypothetical medium the luminiferous ether. The speed c in Maxwell's equations, they believed, was the speed of light relative to the ether. And since the Earth is moving through space, it must be moving through the ether too. So by measuring the speed of light in different directions at different times of year as the Earth orbits the Sun, you should be able to detect the Earth's motion through the ether. You should be able to measure an ether wind. In 1887, two American physicists, Albert Michelson and Edward Morley, set out to do exactly this. They built an incredibly sensitive instrument called an interferometer that could detect tiny differences in the speed of light in different directions. If the Earth was moving through the ether, light traveling in the direction of the Earth's motion should appear to move slightly slower than light traveling perpendicular to it, just as swimming with the current is different from swimming across it. The Michelson-Morley experiment was one of the most precise experiments ever conducted at the time, and the result was nothing. Absolutely nothing. No difference in the speed of light in any direction. No ether wind. No detectable motion through the ether. The speed of light was the same in every direction they measured. This was a crisis, a genuine crisis in physics. Some of the greatest minds of the era tried to explain the result away. The Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently proposed that objects moving through the ether physically contract in the direction of motion in just the right amount to mask the ether wind. This was a clever mathematical fix, and the equations they derived, the Lorentz transformations, would turn out to be incredibly important. But the physical explanation that objects literally shrink because of their motion through the ether felt ad hoc. It felt like patching a sinking ship rather than building a new one. And then, in 1905, a young man changed everything. His name was Albert Einstein. He was 26 years old. He was not a professor at a prestigious university. He was not working in a world-class laboratory. He was a technical expert third class at the Swiss Patent Office in Bern. And in that year, his miracle year, his annus mirabilis, he published 4 papers that would reshape the foundations of physics. One explained the photoelectric effect and helped launch quantum mechanics. One provided definitive evidence for the existence of atoms through the analysis of Brownian motion. One introduced the mass-energy equivalence E equals mc squared, and one, titled On the Electrodynamics of Moving Bodies, introduced the special theory of relativity and demolished the concept of absolute time forever. Einstein's approach was radically different from everyone else's. While other physicists were trying to figure out why the Michelson-Morley experiment could not detect the ether, Einstein asked a different question. What if there is no ether? What if the speed of light really is the same for all observers, regardless of their motion? What if we simply take this at face value and see where the logic leads? Einstein built his entire theory on just 2 postulates, 2 starting assumptions. That is all. The first postulate says that the laws of physics are the same in all inertial reference frames. An inertial reference frame is simply one that is not accelerating, one that is moving at a constant velocity or sitting still. This means that there is no experiment you can do inside a sealed room moving at constant velocity that will tell you how fast you are moving or whether you are moving at all. The laws of physics, all of them, look exactly the same whether you are stationary or cruising at 1,000,000 kilometers per hour, as long as you are not accelerating. The second postulate says that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. This is the revolutionary one. This is the one that breaks everything. Let me make sure you understand how radical this is. Imagine you are standing still and I shine a flashlight past you. You measure the speed of the light and get C, 299,792,458 meters per second. Now, imagine you are flying in a spaceship at half the speed of light, and I shine the same flashlight in the same direction. In Newtonian physics, you would expect to measure the light going at only half of c relative to you because you are chasing it at half of c. But according to Einstein's second postulate, you still measure the speed of that light as di, the full speed of light, no matter how fast you are moving. This seems impossible. This seems like it violates basic arithmetic. If I am moving at half the speed of light, and light is moving at the speed of light, how can the light still appear to move at the full speed of light relative to me? Something has to give, and what gives, what must give, what has no choice but to give, is our notion of space and time themselves. You see, when we say speed, we mean distance divided by time. If the speed of light is always the same, but I am moving, then the distance and the time I measure must be different from the distance and the time you measure. The only way to keep the speed of light constant for all observers is if space and time themselves change, depending on how fast you are moving. This is not a metaphor. This is not a poetic interpretation. This is a logical, mathematical, inescapable consequence of the constancy of the speed of light. And it leads us directly to time dilation. But before we get to the math and the thought experiments, I need to make sure you understand what a reference frame really means, because this concept is crucial to everything that follows. A reference frame is simply a perspective. It is the viewpoint of a particular observer. Imagine you are sitting on a train that is moving at a perfectly smooth, constant speed. You take a ball and toss it straight up into the air. From your perspective, sitting on the train, the ball goes straight up and comes straight down. Simple. But now imagine someone is standing on the platform, watching the train go by. From their perspective, the ball does not go straight up and down. It follows a curved, arc-shaped path because while the ball is in the air, the train and you and your hand have all moved forward. So the ball has moved forward too, tracing out a parabolic trajectory. Who is right? Is the ball going straight up and down, or is it following a curved path? The answer is both. Both descriptions are equally valid. The ball's motion looks different depending on your frame of reference, but the underlying physics, the forces, the laws of motion, they are the same in both frames. Newton's laws work perfectly, whether you calculate from the train frame or the platform frame. This is what the first postulate of relativity is about. No reference frame is special. No reference frame is more correct than any other. They are all equally valid. Now, this is easy to accept when we are talking about a ball on a train. But Einstein showed that the same principle, combined with the constancy of the speed of light, leads to conclusions that are far more dramatic than different trajectories of a ball. It leads to the conclusion that time itself is different in different reference frames. And I am going to show you exactly why, using the most beautiful thought experiment in all of physics, the light clock. Imagine I build a clock, a very special, very simple clock. It consists of just two mirrors, one at the top and one at the bottom, separated by some distance, let us say 1 meter. A pulse of light bounces back and forth between these two mirrors. Every time the light hits the bottom mirror, the clock ticks. One round trip, bottom to top and back to bottom, equals 1 tick. Since we know the speed of light and the distance between the mirrors, we can calculate exactly how long each tick takes. The light travels 2 meters, one up and one down, at the speed of light. So each tick takes a very specific, very precise amount of time. This is our light clock. It is a perfect clock because it is based on the most fundamental constant in the universe, the speed of light. Now, here's where the magic happens. Let us say, I am holding this light clock and I am standing still. You are watching me. From your perspective, the light bounces straight up and straight down, down, tick, up, down, tick. Each tick takes the same amount of time. Nothing surprising here, but now let us say I start moving. I get on a spaceship and I fly past you at a very high speed, let us say 50% of the speed of light. I am still holding my light clock. From my perspective, inside my spaceship, nothing has changed. The light still bounces straight up and straight down, tick, up, down, tick. My clock works perfectly. I notice nothing unusual. But what do you see? You see me and my clock moving to the right at high speed. The bottom mirror sends a pulse of light upward. But by the time that light reaches the top mirror, the entire clock has moved to the right. So from your perspective, the light does not travel straight up. It travels diagonally, going up and to the right. Then the top mirror reflects it back down. But again, by the time it reaches the bottom mirror, the clock has moved further to the right. So the light travels diagonally down and to the right. From your perspective, watching me fly past, the path of the light in my clock is not a straight vertical line. It is a zigzag. 2 diagonal lines forming a V shape, or more precisely, 2 sides of a triangle. Now here is the critical point. The diagonal path is longer than the straight vertical path. If I am stationary, the light goes 1 meter up and 1 meter down. Total 2 meters. If I am moving, the light goes 1 meter up diagonally and 1 meter down diagonally. And because of the diagonal, the total distance is more than 2 meters. The faster I move, the more diagonal the path, and the longer the total distance. Think about it with Pythagoras. The light has to cover the vertical distance between the mirrors, which is unchanged, but also the horizontal distance the clock has moved. The total path is the hypotenuse of a right triangle, and the hypotenuse is always longer than either of the other sides. Now, here comes the crucial universe-altering moment. Remember Einstein's second postulate. The speed of light is the same for all observers. You, standing still, measure the speed of the light in my clock as c, not more than c, not less than c, exactly c. The light in my moving clock is traveling a longer path, but at the same speed. What happens when something travels a longer distance at the same speed? It takes more time. Each tick of my clock, as seen by you, takes longer. My clock, from your perspective, is running slower. And this is not because the clock is broken. It is not because the mechanism has been affected by the motion. It is because the geometry of space-time dictates that the light must travel a longer path in your frame of reference, and since the speed of light is fixed, the tick must take longer. Time itself, as measured by any clock, any process, anything at all, passes more slowly for a moving object. This is time dilation. Let me say that again because it is so important. It is not just the light clock that runs slow. Every clock runs slow. A mechanical clock, a digital clock, a biological clock, the radioactive decay of an atom, the beating of your heart, the firing of neurons in your brain. Every single physical process in the moving frame runs slow as seen from the stationary frame. Because it is not the clocks that are slowing down, it is time. Time itself passes more slowly for the moving object. And here is what makes this even more mind-bending. From my perspective, sitting in my spaceship, I do not feel any of this. My clock ticks normally, my heart beats normally, my thoughts flow at their usual pace. I do not feel sluggish. I do not feel time dragging. To me, everything is perfectly normal. It is only when I compare my clock to yours that I see the discrepancy. And here is the real kicker. From my perspective, it is you who is moving. I am sitting still in my spaceship, and the Earth and you are flying past me at 50% of the speed of light. So from my perspective, it is your clock that is running slow. I look at your clock and I see it ticking more slowly than mine. This seems like a contradiction. I say your clock is slow. You say my clock is slow. Who is right? The answer, the beautiful, bizarre, counterintuitive answer, is that both of us are right. Both perspectives are equally valid. Time dilation is symmetric in special relativity. As long as we are both moving at constant velocities relative to each other, neither of us can claim to be the one who is truly at rest. We each see the other's clock running slow. And there is no contradiction because we are making our measurements from different reference frames, and there is no universal reference frame that can settle the dispute. Now, I know what you might be thinking. That sounds like it should cause a paradox. And it does, or at least it seems to. We will get to the famous twin paradox soon, and I will resolve it completely. But first, let me give you the mathematical formula so you can see just how dramatic time dilation becomes at high speeds. The amount of time dilation is given by a factor called gamma, the Lorentz factor. Gamma equals 1 divided by the square root of 1 minus vi, squared over c squared. Here, v is the speed of the moving object and c is the speed of light. When v is 0, gamma is 1. No time dilation. When v is small compared to c, gamma is very close to 1. Very little time dilation. But as v approaches c, gamma grows without limit. Let me walk you through some numbers so you can feel this. At 10%, the speed of light, which is about 30,000 kilometers per second, an absolutely blistering speed by any human standard, gamma is approximately 1.005. This means a clock moving at 10% of c runs about 0.5% slower. You would barely notice it even with precise instruments. At 50% the speed of light, gamma is about 1.155. Now the moving clock runs about 15% slower. For every hour that passes on the stationary clock, only about 52 minutes pass on the moving clock. That is starting to be significant. At 87% the speed of light, gamma is approximately 2. This is a landmark number. At this speed, time passes at half the rate. For every hour you experience, the moving observer experiences only 30 minutes. 2 to 1. At 99% the speed of light, gamma is about 7.09. At this speed, for every 7 hours you experience, the moving observer experiences only 1 hour. The effect is now dramatic. At 99.9% the speed of light, gamma is about 22.4. At 99.99%, gamma is about 70.7. At 99.9999%, gamma is about 707. And as v approaches c, as you get closer and closer to the speed of light, gamma approaches infinity. Do you see what is happening? At everyday speeds, the speeds we experience in our daily lives, time dilation is so incomprehensibly small that it is completely undetectable without the most precise instruments ever built. This is why Newton's absolute time works so well for everyday life. This is why we never notice it. A car traveling at 100 kilometers per hour experiences time dilation of roughly 0.000000000000001%. Even an airplane at 900 kilometers per hour, even the fastest rocket humanity has ever built. The time dilation effects are tiny. Our brains evolved in a world where nothing moves anywhere close to the speed of light. So, of course, our intuition tells us time is absolute. But the effect is real. It is always there. And at high enough speeds, it becomes dramatic, transformative, reality-altering. Now, at this point, I want to pause and check in with you. We have covered a lot of ground already. We have gone from the simple ticking of a clock to the complete demolition of absolute time. We have seen how the constant speed of light logically forces time to be different for different observers. We have seen the light clock thought experiment. We have seen the mathematical formula. If your mind is already starting to feel stretched, good. That is exactly what should be happening, because we are just getting started. The real craziness is coming. So if you have not yet hit that like button, please do it now. It genuinely helps this video reach more people who are curious about the universe. And drop a comment below. Tell me, has your understanding of time already changed? Are you starting to see time differently? I want to know what you are thinking right now. Now let me move from theory to evidence. Because a theory, no matter how elegant, no matter how beautiful, is nothing without experimental verification. And the experimental evidence for time dilation is overwhelming. It is not just one experiment. It is dozens. It is hundreds. It is the accumulated evidence of a century of increasingly precise measurements, every single one of which confirms exactly what Einstein predicted. Let me take you through some of the most important and most striking experiments. We already briefly mentioned the Haffley-Keating experiment, but let me go into more detail, because it is one of the most wonderfully direct tests of time dilation ever performed. In October of 1971, Joseph Haffel, a physicist at Washington University, and Richard Keating, an astronomer at the United States Naval Observatory, took 4 cesium beam atomic clocks, packed them up, and took them on a trip around the world. Not in a special laboratory aircraft, not in a military jet, on regular commercial airlines. They bought tickets. They sat in seats. They had their atomic clocks sitting in the seats next to them. The flight attendants must have had questions. They flew one set of clocks eastward around the world and another set westward. Now this is important. The Earth is rotating. When you fly eastward, you are flying in the same direction as the Earth's rotation, so your total speed, relative to the center of the Earth, is the speed of the airplane plus the rotational speed of the Earth's surface. When you fly westward, you are flying against the Earth's rotation, so your total speed relative to the center of the Earth is smaller. This means the eastward flying clocks were effectively moving faster than the ground clocks, and the westward flying clocks were effectively moving slower. Special relativity predicts that the faster moving eastward clocks should lose time relative to the ground clocks, and the slower moving westward clocks should gain time. But there is also a general relativistic effect because the airplanes are at a higher altitude, where gravity is slightly weaker. and we will talk more about gravitational time dilation later. Taking both effects into account, Einstein's theories predicted that the eastward clocks should lose about 40 nanoseconds, and the westward clocks should gain about 275 nanoseconds relative to the ground clocks. When Hafele and Keating brought their clocks back and compared them, the eastward clocks had lost 59 nanoseconds, and the westward clocks had gained 273 nanoseconds. Within the experimental uncertainty, this was perfect agreement with relativity. Two guys with atomic clocks on commercial flights proved that time is not absolute. The moving clocks ran at different rates. Time dilation is real. But that is just one experiment. Let me tell you about another one that I find even more elegant because it involves not man-made clocks, but nature itself providing the evidence. This experiment involves particles called muons. A muon is a subatomic particle, similar to an electron, but about 207 times heavier. Muons are unstable. They decay. They fall apart, with a half-life of about 2.2 microseconds. That means if you start with a bunch of muons, after 2.2 microseconds, half of them will have decayed. After another 2.2 microseconds, half of the remaining ones will have decayed, and so on. Muons are created high in the Earth's atmosphere, about 10 kilometers up, when cosmic rays, high-energy particles from space, slam into air molecules. These atmospheric muons are created moving at very high speeds, typically about 99.8% of the speed of light. Now let us do some arithmetic. At 99.8% the speed of light, a muon travels about 299,500 kilometers per second. In 2.2 microseconds, it would travel about 660 meters. Even if we generously give it several half-lives, say 10 microseconds, it would travel about 3 kilometers. But the muons are created 10 kilometers up. By the time they reach the ground, by all rights, essentially all of them should have decayed. We should detect almost no muons at sea level. But we detect lots of them, lots and lots of them, far more than we would expect if time were passing at the normal rate for the muons. And the explanation is time dilation. The muons are moving at 99.8% the speed of light. At that speed, gamma is about 15.8. From our perspective on the ground, the muons' internal clocks are running about 15.8 times slower. Their half-life, as we measure it, is not 2.2 microseconds, but about 34.8 microseconds. That is enough time for them to travel 10 kilometers and reach the ground. Time dilation keeps them alive long enough to make the journey. And here is the beautiful thing. From the muon's perspective, time is passing normally. The muon still decays in 2.2 microseconds of its own time. But from the muon's perspective, it is not time that is different, it is space. The distance from the top of the atmosphere to the ground, which is 10 kilometers in our frame, is length contracted in the muon's frame. The muon sees the atmosphere as being only about 630 meters thick, so it has no trouble traversing this short distance in its brief lifetime. Two perspectives, two descriptions, one reality. The math works out perfectly either way. This is the self-consistency of relativity. It does not matter which frame you analyze the situation from. You get the same physical answer. The muons reach the ground. Whether you explain it as time dilation from the ground perspective or length contraction from the muon perspective, the result is the same. And both explanations are equally true. This is not just a historical experiment. We can measure this today with extraordinary precision. We can measure the arrival rate of muons at different altitudes and compare it to the predictions of relativity. And the agreement is stunning. Every measurement confirms that the muons' lifetimes are extended by exactly the factor gamma. This is time dilation, writ in the behavior of fundamental particles with no room for doubt. And if atmospheric muons are not enough to convince you, let us talk about particle accelerators. At CERN, the European Organization for Nuclear Research, near Geneva, Switzerland, the Large Hadron Collider accelerates protons to 99.9999991% the speed of light. At this speed, gamma is about 7,454. Inside the accelerator, unstable particles are created in the collisions, and these particles, which should decay in microseconds, persist for milliseconds. They live thousands of times longer than they would at rest, and they do so by exactly the factor that relativity predicts. Every single time, in every single experiment. For over half a century, at particle accelerators around the world, time dilation has been confirmed in thousands upon thousands of measurements. It is one of the most thoroughly tested predictions in all of physics. It is as solid as the ground beneath your feet. More solid, actually, because the ground is just a thin crust floating on molten rock, while time dilation is a fundamental property of the universe. Now, let me return to the GPS example because it is so beautifully practical and it ties together multiple aspects of what we are discussing. The global positioning system consists of a constellation of about 31 satellites orbiting the Earth at an altitude of approximately 20,200 kilometers, moving at about 14,000 kilometers per hour. Each satellite carries extremely precise atomic clocks. To determine your position, your GPS receiver gets signals from multiple satellites and measures the time it took for each signal to arrive. Since the signals travel at the speed of light, the receiver can calculate how far away each satellite is and, by triangulation, figure out where you are. For this to work, the satellite clocks need to be accurate to within about 20 to 30 nanoseconds. Any larger error and your position calculation starts to drift unacceptably. But here is the problem. The satellite clocks are subject to two relativistic effects. First, because the satellites are moving relative to the ground, special relativistic time dilation causes their clocks to run slower. This effect amounts to about -7 microseconds per day. The satellite clocks fall behind by 7 microseconds each day due to their speed. Second, because the satellites are higher up, further from the center of the Earth, they are in a weaker gravitational field. We have not discussed gravitational time dilation in detail yet, but the key fact is this: clocks in weaker gravity run faster. This general relativistic effect amounts to about +45 microseconds per day. The satellite clocks get ahead by 45 microseconds each day due to the weaker gravity at their altitude. The net effect is that GPS satellite clocks gain about 38 microseconds per day compared to ground clocks. 38 microseconds does not sound like much, but remember, light travels about 300 meters in 1 microsecond. So 38 microseconds corresponds to about 11.4 kilometers. If this correction were not applied, GPS positions would drift by about 10 to 11 kilometers per day. Within a week, GPS would be off by nearly 80 kilometers. It would be completely useless. So the engineers who designed the GPS system had to take Einstein's theories into account. The satellite clocks are pre-adjusted before launch to tick at a slightly different rate, compensating for the expected relativistic effects. And additional corrections are applied in real time. Every time you use GPS, every single time, the system is applying corrections based on both special and general relativity. You are a daily user of Einstein's theories. You just never knew it. I find this extraordinary. There is something deeply poetic about the fact that the most abstract, most counterintuitive theory in physics, the one that tells us time is not what we think it is, the one that says moving clocks run slower and gravity bends time, has such a mundane, everyday application. It lives in your phone. It guides you to the nearest coffee shop. Einstein's universe is not some abstract mathematical playground. It is the world you live in right now, today. The strangeness is everywhere. You just have to know where to look. Let me share another incredible fact with you before we move on. In 2010, researchers at the National Institute of Standards and Technology, NIST, used aluminum quantum logic clocks, which are accurate to about 1 second in 3.7 billion years, to measure time dilation due to a height difference of just 33 centimeters, 1 foot. They placed one clock 33 centimeters higher than another and measured that the higher clock ticked slightly faster. They could detect the gravitational time dilation between your feet and your head. Your head, right now, is aging faster than your feet. Not by much. By an unfathomably tiny amount, but the effect is real. It is measurable. It is there. And here is another one. Because of gravitational time dilation, the core of the Earth, which is deeper in Earth's gravitational well, has experienced less time than the surface. Over the 4.5 billion year history of the Earth, the core is about 2.5 years younger than the surface. The center of the planet you live on is younger than the ground you walk on. Not by much, but by a real, calculated, physically meaningful amount. These are not speculations. These are not approximations. These are precise, experimentally verified facts about the nature of time. And every single one of them confirms what Einstein told us in 1905 and 1915. Time is not absolute. Time is relative. Moving clocks run slower. Clocks in stronger gravity run slower, and it is not an illusion. Now we need to confront the elephant in the room. The most famous puzzle in all of relativity. The thought experiment that has confused more physics students, launched more heated arguments, and generated more incorrect explanations than perhaps any other concept in the subject. I am talking about the twin paradox. Here is the setup. Two identical twins, let us call them Alice and Bob. They are the same age, born at the same moment. Alice stays on Earth. Bob gets on a spaceship. Bob's spaceship accelerates to 90% of the speed of light and heads toward a distant star, let us say one that is 10 light years away. At 90% of C, gamma is approximately 2.29. Bob travels for what feels to him like about 4.8 years to reach the star. Then he turns around and comes back at the same speed. The return trip also takes him about 4.8 years of his time. So from Bob's perspective, the total trip took about 9.6 years. He is 9.6 years older when he returns. But from Alice's perspective on Earth, things are different. She sees Bob traveling at 90% of c to a star that is 10 light years away. At that speed, the trip takes 10 divided by 0.9, which is about 11.1 years each way, for a total of about 22.2 years. When Bob returns, Alice is 22.2 years older. So when Bob steps off his spaceship and hugs his twin sister, they are no longer the same age. Bob is 9.6 years older than when he left. Alice is 22.2 years older than when he left. Alice has aged more than twice as much as Bob. This is not a prediction of some fringe theory. This is the straightforward, unambiguous prediction of special relativity, confirmed by every relevant experiment ever performed. But here is where the paradox comes in, or at least where it seems to come in. Remember what we said earlier. In special relativity, time dilation is symmetric. If I see your clock running slow, you see my clock running slow. So from Bob's perspective, he is the one who is stationary, and it is Earth that is flying away from him at 90% of c. From Bob's frame, it is Alice's clock that should be running slow. So should not Bob predict that when they reunite, Alice will be younger? If both perspectives are equally valid, who is really younger? This seems like a genuine paradox. Two contradictory predictions from the same theory. But it is not a paradox. It is a misunderstanding, and the resolution is both simple and profound. The key insight is this: the situation is not symmetric. Alice and Bob are not in equivalent situations. Alice stays in one inertial reference frame the entire time. She sits on Earth, which for our purposes we can treat as approximately inertial, and she never accelerates, never changes her state of motion. She remains in a single reference frame from beginning to end. Bob, on the other hand, does not stay in one inertial frame. He starts at rest on Earth. Then he accelerates to 90% of c. Then, when he reaches the star, he decelerates, turns around, accelerates back to 90% of t in the opposite direction, and then decelerates again when he reaches Earth. Bob changes reference frames. He accelerates. He feels forces. If he were holding a cup of coffee during the turnaround, it would slosh. He can feel physically that something happened. He can distinguish his experience from Alice's. This is the crucial difference. Special relativity says that all inertial reference frames are equivalent. It does not say that accelerating reference frames are equivalent to inertial ones. Bob's experience includes acceleration, which breaks the symmetry. And when you properly account for the acceleration, when you do the full calculation, the answer is unambiguous. Bob ages less. Alice ages more. There is no paradox. Let me explain this in another way that might be even more illuminating. Think about space-time, the four-dimensional fabric that combines 3 dimensions of space with 1 dimension of time. In space-time, every object traces a path called a world line. Alice, sitting on Earth, traces a straight world line through space-time. She stays in one place in space and moves forward in time. Her world line is a straight vertical line on a space-time diagram. Bob, who travels out and comes back, traces a bent world line. His world line goes out at an angle, representing his motion through space, then bends at the turnaround point and comes back at an angle, representing his return. His world line is like 2 sides of a triangle. Now here is the counterintuitive part. In ordinary space, a straight line is the shortest distance between 2 points. But in space-time, because of the way the geometry works, because space-time has a different kind of geometry than regular space, a geometry called Minkowski geometry. A straight world line corresponds to the maximum proper time between two events. Proper time is the time experienced by the person following that world line. So Alice, following the straight world line, experiences the most time. Bob, following the bent world line, experiences less time. This is the space-time version of the triangle inequality, and it runs opposite to what we expect in ordinary space. This is not hand-waving. This is precise mathematics. You can calculate it exactly, and the answer matches every experiment ever performed. The traveling twin ages less. The stay-at-home twin ages more. The twin who accelerates, who changes frames, who follows a non-straight path through space-time is the one who experiences less time. Always. Now, let me make this more vivid with some more dramatic scenarios. The Alpha Centauri trip at 90% of C is interesting, but let us push it further. Imagine traveling to the center of the Milky Way galaxy, which is about 26,000 light-years away. If you could travel at 99.99% of the speed of light, gamma would be about 70.7. The trip would take about 26,000 years as measured by people on Earth, but the traveler would experience only about 368 years. Still far too long for a human lifetime, but vastly less than the Earth time. Now push it even further. Travel at 99.9999% of the speed of light. Gamma is now about 707. That same trip to the galactic center would take about 37 years for the traveler. You could leave Earth as a young adult and arrive at the center of the galaxy as a senior citizen. But 26,000 years would have passed on Earth. Every person you ever knew, every building you ever entered, every civilization you were part of, gone. 26 millennia of history would have unfolded in your absence. And if you really want to go wild, consider this. If you could sustain a constant acceleration of 1g, the same as the gravity you feel right now, you could reach astonishingly far in a human lifetime. At 1g of constant acceleration for the first half of the trip, and 1g of deceleration for the second half, you could reach the Andromeda Galaxy, 2.5 million light-years away, in about 28 years of ship time. 28 years. You would arrive at a galaxy 2.5 million light-years away in less than 3 decades. But on Earth, 2.5 million years would have passed. Homo sapiens might not even exist anymore. Whatever civilization remains on Earth would be unrecognizably different from the one you left. You could, in principle, traverse the entire observable universe in a single human lifetime. If you could somehow sustain a constant 1g acceleration, and if you had a source of energy capable of powering such a journey, you would arrive at the edge of the observable universe having aged perhaps 45 years. But on Earth, billions of years would have passed. The sun might have already died. Earth might be a burned cinder. The entire history of your species, your planet, your star, would have played out while you were traveling. This is what time dilation means at its most extreme. It means that the universe is, in a sense, accessible to an individual human being. You could theoretically see it all, but the cost is total separation from everything and everyone you have ever known. It is a kind of one-way time travel, forward into the future with no way back. You cannot go home again. Not really, because home as you knew it will be gone. I want to sit with that for a moment. This is not science fiction. This is not a writer's imagination. This is what the equations of physics tell us is possible. The mathematics is clear. The experiments confirm it. If we ever develop the technology to travel at a significant fraction of the speed of light, this will be the reality that astronauts face. Leave Earth, explore the stars, come back to find your world centuries or millennia in the future. It is breathtaking, it is heartbreaking, it is physics. Would you do it? If you were offered a seat on a ship that could take you to see a black hole up close, to visit another star system, to witness the wonders of the cosmos firsthand, but at the cost of everyone you love aging and dying while you were gone, would you go? Think about that, and tell me your answer in the comments. I genuinely want to know. Because this is not just a thought experiment. One day, this could be a real choice that real human beings have to make. Now, this video has taken an enormous amount of research and effort to put together. If you are learning something new, if your mind is being stretched, if you are seeing the universe differently, please share this video with someone who loves science. Send it to a friend. Post it on your social media. Let us spread this knowledge as far as we can. And if you have not liked this video yet, please do. It makes a real difference in helping this content reach more curious minds around the world. Now let us move on to something we have touched on several times, but not yet fully explored. When we discussed the muon experiment, I mentioned that from the muon's perspective, it is not time that is different, but space. The muon sees the distance to the ground as being shorter. This phenomenon is called length contraction, and it is the spatial counterpart to time dilation. They are two sides of the same coin, two manifestations of the same underlying reality, that space-time is different in different reference frames. Length contraction says this: an object moving relative to you appears shortened in the direction of its motion. Not in the directions perpendicular to its motion, only in the direction it is moving. The formula is straightforward. The contracted length equals the rest length divided by gamma. So if a spaceship is 100 meters long at rest and it flies past you at 87% of the speed of light, where gamma is 2, you measure it as only 50 meters long. At 99.5% the speed of light, gamma is about 10, and the spaceship appears to be only 10 meters long. At 99.995%, gamma is 100, and the spaceship appears to be only 1 meter long. Just like time dilation, the moving observer does not experience anything unusual. If you are inside the spaceship, everything feels normal. Your ship is 100 meters long. Your rooms are the same size. Your coffee table is the same shape. It is only from the perspective of someone you are moving relative to that the contraction appears. And just like time dilation, length contraction is symmetric. If you see me contracted, I see you contracted. Neither of us is really contracted. Contraction is a relationship between frames, not an absolute property. Now, length contraction and time dilation are deeply connected. They have to be. They are both consequences of the same postulates, and they conspire to keep the speed of light constant for all observers. The muon example shows this beautifully. From our frame, the muon's time is dilated, so it lives longer and can reach the ground. From the muon's frame, its time is normal, but the distance to the ground is contracted, so it has a shorter distance to travel. Both perspectives predict the same physical outcome, muons reaching the ground. The self-consistency is perfect. There is a common question that comes up at this point. If a moving object is length contracted, what would it actually look like? Would you see it squished, like a pancake? The answer is more interesting than you might expect. In 1959, the physicist Roger Penrose and independently James Turrell showed that what you would actually see is not a squished object, but a rotated one. This is called the Turrell-Penrose rotation. The reason is that you see an object by the light that reaches your eyes, and light from different parts of the object left at different times, because it had to travel different distances to your eyes. This creates a kind of visual illusion, where the contracted object appears to be rotated rather than squished. The full visual experience of looking at relativistic objects is extraordinary. Objects approaching you would appear compressed and blue-shifted, while objects receding would appear stretched and red-shifted. The star field ahead of a near-light-speed ship would compress into a bright circle ahead of you, with all the stars appearing to cluster toward the direction of travel, while the star field behind would spread out and dim. It is a profound distortion of the visual field that no human has ever experienced, but that computer simulations can now render in stunning detail. Now, there is one more aspect of special relativity's effect on speed that we need to address directly. Why can nothing with mass reach the speed of light? This is one of the most frequently asked questions in physics, and the answer connects beautifully to everything we have been discussing. Think about it from the perspective of the time dilation formula. As the speed v approaches c, gamma approaches infinity. This means the time dilation becomes infinite. A clock moving at the speed of light, if such a thing were possible for an object with mass, would not tick at all. Time would stop. But what does it take to get there? As you accelerate an object, trying to push it closer and closer to the speed of light, something peculiar happens. It gets harder and harder to accelerate. Not because of friction, not because of drag, but because of the fundamental structure of spacetime. The energy required to accelerate an object increases as it goes faster, and as v approaches c, the energy required approaches infinity. You would need an infinite amount of energy to accelerate even the tiniest grain of sand to the speed of light. And infinite energy does not exist. This is sometimes described in terms of relativistic mass, the idea that an object's effective mass increases as it goes faster. While this concept is somewhat outdated in modern physics pedagogy, most physicists prefer to talk about relativistic momentum and energy rather than relativistic mass. The intuition it gives is useful. The faster you try to push something, the harder it pushes back, because more and more of the energy you put in goes into increasing the object's energy content rather than its speed. The speed of light is not just a speed limit in the way that a highway speed limit is a speed limit, where you could go faster, but you are not supposed to. The speed of light is a speed limit built into the fabric of reality itself. It is the maximum speed at which any information, any influence, any causal effect can propagate through the universe. It is not that we have not built a fast enough engine. It is that the structure of space-time geometrically prevents it. Photons, particles of light, travel at the speed of light because they have zero rest mass. They do not need to be accelerated to c. They are born traveling at c, and they cannot travel at any other speed. Every photon that has ever existed has traveled at exactly the speed of light. And here is a truly mind-bending consequence. From the perspective of a photon, if we could even define such a perspective, which is mathematically tricky because the Lorentz transformations are undefined at v equals IC. But if we extrapolate, the photon experiences zero time. The moment of its creation and the moment of its absorption are, in a sense, the same moment. A photon from a distant star, one that has traveled for millions of years, from our perspective, experiences no time at all. It is emitted and absorbed in the same instant, from its own perspective. The entire history of the universe, all the billions of years, all the expansion of space, all the formation of galaxies and stars and planets is, for a photon, happening all at once. I think there is something profoundly beautiful about that. Something almost mystical, though it is hard, cold physics. The particles that bring us light, that carry information from the farthest reaches of the cosmos, that allow us to see the universe, these particles experience no time. They exist in a kind of eternal now. Make of that what you will. Let us shift gears now and enter the domain of general relativity. Everything we have discussed so far has been special relativity, Einstein's 1905 theory that deals with constant velocity motion and the effects of speed on time and space. But special relativity was only the first chapter. The full story, the complete picture, required Einstein to grapple with something that special relativity deliberately left out: gravity. After publishing Special Relativity in 1905, Einstein was not satisfied. He knew that his theory was incomplete. Special relativity applied only to inertial reference frames, frames moving at constant velocity with no acceleration. But gravity causes acceleration. Objects fall. The Earth orbits the Sun. The Moon orbits the Earth. All of this involves acceleration, and special relativity had nothing to say about it. Worse, Newton's theory of gravity was incompatible with special relativity. Newton's gravity was instantaneous. The gravitational influence of the Sun reached the Earth at infinite speed, which violated the principle that nothing can exceed the speed of light. Einstein needed a new theory of gravity, and it took him 10 years of grueling work to find it. 10 years of struggle, false starts, dead ends, and moments of despair, but also moments of transcendent insight. One such moment, which Einstein later called the happiest thought of my life, came in 1907. He was sitting in his chair at the patent office when it occurred to him, if a person falls freely, they do not feel their own weight. Think about that. If you are in an elevator and the cable breaks and you are in free fall, you are weightless. You float. A ball released from your hand does not fall to the floor, it floats next to you. Inside the free-falling elevator, there is no experiment you can do that will tell you that you are in a gravitational field. Everything behaves as if gravity does not exist. Conversely, imagine you are in a rocket ship in deep space, far from any planet or star, and the rocket is accelerating at 1g. You feel pressed to the floor. If you drop a ball, it falls to the floor. If you stand on a scale, it reads your normal weight. Inside the accelerating rocket, everything behaves exactly as if you are standing on the surface of the Earth. You cannot tell the difference. This is the equivalence principle. Gravity and acceleration are locally indistinguishable. This was Einstein's great insight, and it led him over the next 8 years to a completely new understanding of gravity. Not as a force acting between objects, as Newton described it, but as the curvature of space-time caused by mass and energy. The idea, expressed in the simplest possible terms, is this. Mass and energy tell spacetime how to curve, and curved spacetime tells objects how to move. This is the essence of general relativity. Gravity is not a force pulling you toward the Earth. Gravity is the curvature of space-time around the Earth, and you are simply following the straightest possible path through that curved space-time. This straightest possible path is called a geodesic. Think of the classic analogy. Imagine a flat, stretched rubber sheet. Place a heavy bowling ball in the center. The sheet deforms, creating a dip around the bowling ball. Now roll a marble across the sheet. The marble will curve toward the bowling ball, not because the bowling ball is pulling it with some invisible force, but because the marble is following the curved surface of the sheet. This is not a perfect analogy, because space-time curvature is four-dimensional and involves time as well as space. But it gives you the right intuition. Massive objects curve the fabric of space-time around them, and other objects follow curves through that warped fabric. Now here's where this connects to our story about time. When space-time is curved, time is affected. Specifically, clocks closer to a massive object, deeper in a gravitational well, tick more slowly than clocks further away. This is gravitational time dilation, and it is a direct consequence of general relativity. This is a distinct effect from the velocity-based time dilation of special relativity. In special relativity, it is your speed that causes time dilation. In general relativity, it is the gravitational field you are in. A clock sitting on the surface of the Earth ticks more slowly than a clock on top of a mountain, which in turn ticks more slowly than a clock in orbit, which ticks more slowly than a clock in deep space far from any massive object. The stronger the gravitational field, the more time slows down. The formula for gravitational time dilation near a spherical mass is T equals T0 times the square root of 1 minus 2 gm over rc squared, where g is the gravitational constant, m is the mass of the object, r is the distance from the center of the object, and c is the speed of light. As r decreases, as you get closer to the mass, the factor under the square root gets smaller, and time passes more slowly. As the factor approaches zero, time dilation becomes infinite. Let me give you some concrete examples so you can feel the magnitude of this effect. On the surface of the Earth, gravitational time dilation is extremely small but measurable. A clock at sea level runs about 1 part in 10 to the power of 16, slower than a clock in deep space. That is about 1 microsecond per 30 years. Tiny, but modern atomic clocks are so precise that they can measure this effortlessly. On the surface of the Sun, the effect is larger. Time on the surface of the Sun runs about 2 seconds slower per century compared to a clock in deep space. Still small, but noticeably larger than on Earth. On the surface of a white dwarf, a stellar remnant with a mass similar to the Sun but compressed to the size of the Earth, the effect becomes more substantial. Time on a white dwarf might run several minutes slower per year compared to a clock far away. On the surface of a neutron star, which is even more extreme, with a mass of about 1.4 solar masses crammed into a sphere only about 20 kilometers across, time can run 20 to 30% slower. A clock on a neutron star, if such a thing could survive the intense gravity, would tick significantly slower than a clock in deep space. An observer far away would see everything on the neutron star happening in slow motion. And then there are black holes. At a black hole, the curvature of space-time becomes so extreme that it creates a point of no return, the event horizon. At the event horizon of a black hole, gravitational time dilation becomes infinite. A clock falling toward a black hole would appear to a distant observer to tick more and more slowly as it approaches the event horizon. The observer would never actually see the clock cross the event horizon. It would appear to slow down asymptotically, getting closer and closer to the horizon, but never quite reaching it, while the light from it would become increasingly red-shifted, dimmer and dimmer, until it fades from view. From the perspective of the clock itself, the person falling into the black hole, nothing unusual happens at the event horizon. They cross it in finite time by their own clock. But they cannot communicate this fact to anyone outside, because no signal can escape from within the event horizon. The event horizon is the surface inside which escape would require faster-than-light travel, which is impossible. If you could somehow hover just outside the event horizon of a massive black hole, time would pass extraordinarily slowly for you. Compared to the rest of the universe, you could watch the far future of the cosmos unfold in fast forward. Stars being born and dying, galaxies colliding, civilizations rising and falling, all in what feels like a short time to you. The most extreme time machine in the universe is a black hole. You might recognize this from the movie Interstellar, directed by Christopher Nolan, with scientific consulting by the physicist Kip Thorne. In the movie, the protagonists visit a planet orbiting very close to a supermassive black hole called Gargantua. Because of the intense gravitational time dilation, 1 hour on the surface of the planet corresponds to 7 years back on the spaceship orbiting farther away. This is real physics. Kip Thorne worked out the numbers, and while the specific scenario requires some extreme conditions, the underlying principle is absolutely correct. Time near a black hole is drastically dilated relative to time far away. The movie got the science right. Now here is something that really unites special and general relativity in a beautiful way. We talked about the GPS satellites earlier, and I mentioned that there are two relativistic effects at play. The satellites' speed causes their clocks to run slow by about 7 microseconds per day. This is special relativistic time dilation. But the satellites' altitude, their position higher in Earth's gravitational well, where gravity is weaker, causes their clocks to run fast by about 45 microseconds per day. This is general relativistic gravitational time dilation. The two effects work in opposite directions. The velocity effect slows the clocks down. The gravitational effect speeds them up. And the net result, the gravitational effect being larger, is that the satellite clocks run about 38 microseconds per day fast compared to ground clocks. This is a gorgeous example of both types of time dilation operating simultaneously in a real, practical system. And it shows that both effects are absolutely real and must be accounted for. You cannot ignore either one. The universe demands that you reckon with both special and general relativity. There is no way around it. Let me also mention the Pound-Rebka experiment, which was one of the first direct confirmations of gravitational time dilation. In 1959, Robert Pound and Glenn Rebka, working at Harvard University, measured the gravitational redshift of gamma rays traveling up a 22.5-meter tower. The gamma rays emitted at the bottom of the tower had to climb up through the Earth's gravitational field to reach a detector at the top. General relativity predicted that the gamma rays would lose a tiny amount of energy in climbing, which would shift their frequency to the red lower frequency end of the spectrum. The predicted shift was absolutely minuscule, about 2 parts in 10 to the 15th power. But Pound and Rebka, using a technique called Nussbauer spectroscopy, managed to measure it, and their result agreed with Einstein's prediction to within 10%. Later refinements of the experiment achieved agreement to within 1%. Gravitational time dilation is real. Clocks at the bottom of a tower run slower than clocks at the top, even on Earth, even over a distance of just 22.5 meters. At this point, I want to take a step back and appreciate the full picture of what we have established. Time dilation comes in 2 flavors: velocity-based time dilation from special relativity. The faster you move, the slower your clock ticks relative to a stationary observer. Gravitational time dilation from general relativity. The deeper you are in a gravitational field, the slower your clock ticks relative to someone further from the mass. Both effects are real. Both are experimentally confirmed, and both arise from the same underlying truth. Space-time is not the rigid absolute stage that Newton imagined. Space-time is dynamic, flexible, responsive to motion and mass and energy. It curves and stretches and warps. And time, as a dimension of space-time, curves and stretches and warps along with it. There is actually a deep unity between these 2 types of time dilation. In the framework of general relativity, which encompasses special relativity as a special case, both effects are manifestations of the geometry of space-time. A straight path through space-time, a geodesic, corresponds to the maximum proper time between 2 events. Any deviation from this path, whether caused by acceleration, velocity, or the curvature due to gravity, results in less proper time. The traveling twin ages less because their world line through space-time is not a geodesic. A clock near a massive object ages less because the curvature of space-time near the mass distorts the geometry. It is all geometry. It is all the shape of space-time. Einstein reduced all of physics, all of gravity, all of the behavior of time to geometry. And that is perhaps his greatest achievement. Now let us dive into the philosophical implications of what we have discovered, because time dilation is not just a physical phenomenon. It is a window into the deepest questions about the nature of reality. The first and most immediate philosophical consequence of time dilation is the death of universal simultaneity. In Newton's universe, there was a clear objective, universal now. At any given moment, there was a fact of the matter about what was happening everywhere in the universe at that moment. Events could be unambiguously classified as happening at the same time or at different times. This is not true in Einstein's universe. Consider this thought experiment, often attributed to Einstein himself. Imagine a train moving at high speed. In the exact middle of the train, there is a light source. At the moment the light is turned on, 2 flashes of light are emitted simultaneously, one toward the front of the train and one toward the back. For a passenger sitting in the middle of the train, both flashes reach the front and back walls at the same time. The flashes are simultaneous. But for an observer standing on the platform, watching the train go by, the back wall of the train is moving toward the rearward flash, while the front wall is moving away from the forward flash. Since the speed of light is the same in both directions for the platform observer, the rearward flash reaches the back wall first, and the forward flash reaches the front wall later. The two events that were simultaneous for the train passenger are not simultaneous for the platform observer. This is the relativity of simultaneity, and it is devastating for the idea of a universal now. Two events that happen at the same time for one observer happen at different times for another observer, and neither observer is wrong, neither observer is mistaken. Both are equally correct. There is simply no universal observer-independent fact about whether two distant events happen at the same time. Simultaneity is relative. Now is relative. The present moment is relative. Think about what this means. Right now, as you sit there watching this video, you might think there is a fact of the matter about what is happening right now on a planet orbiting Alpha Centauri, 4.3 light-years away. But there is not. Different observers, moving at different speeds, would disagree about what is happening now on that distant planet. For some observers, the events happening now, there are what we would call next year. For other observers, they are what we would call last year. The very concept of now across large distances is meaningless in an absolute sense. This leads to a philosophical viewpoint sometimes called the block universe or eternalism. If there is no universal now, if the past, present, and future are not objectively defined categories but are observer-dependent, then perhaps the universe does not really flow from past to future. Perhaps the universe simply exists timelessly as a four-dimensional block of spacetime, with all events, past, present, and future, equally real. We experience time as flowing because of our particular perspective, our particular world line through the block, but the flow is an illusion. All of space-time, all of history is just there. This is a profound and disquieting idea. If the block universe is real, then the future already exists. It is already there, just as the past is already there. The future is not open. It is not undetermined. It is as fixed as the past. We simply have not reached it yet along our world line, but it exists timelessly in the block of space-time. Einstein himself seems to have leaned toward this view. After the death of his close friend Michel Besso in 1955, just weeks before his own death, Einstein wrote a letter to Besso's family. He said, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. A stubbornly persistent illusion, that is what Einstein believed about the flow of time. Not that it was unreal in some vague philosophical sense, but that his own physics, his own equations, told him that the distinction between past, present, and future has no objective, observer-independent meaning. Now, I want to be clear. Not all physicists accept the block universe interpretation. There are other interpretations of relativity that preserve a sense of becoming, of genuine temporal flow. The presentist view holds that only the present moment is real, despite the challenges that relativity poses for defining a universal present. The growing block view holds that the past and present are real, but the future is not yet determined. These are active philosophical debates, and they are far from settled. But what is settled, what is beyond dispute, is that time is not what our everyday experience suggests. Time is not a universal river flowing at the same rate for everyone. It is flexible. It is relative. It is entangled with space in ways that our brains did not evolve to comprehend intuitively. Whatever the correct philosophical interpretation turns out to be, the physical facts of time dilation are not going away. Now, there is another question that time dilation naturally leads to, and it is one that has captivated human imagination for centuries. Is time travel possible? The answer, perhaps surprisingly, is yes, in one direction. We are all time travelers, moving forward through time at a rate of 1 second per second. But time dilation gives us the ability to travel forward through time faster than the normal rate. We have already seen this. The traveling twin ages less than the stay-at-home twin. The traveling twin effectively jumps forward in time. If you travel at 99% of the speed of light for 1 year of your time, you arrive in a world that is about 7 years in your future. You have time traveled forward by 6 years. This is real. This is achievable in principle. It is just very, very hard from an engineering standpoint. What about backward time travel? Can we go into the past? This is where things get much more speculative and much more problematic. General relativity does mathematically allow for solutions that contain what are called closed time-like curves, paths through spacetime that loop back to their own starting point in time. In 1949, the logician Kurt Gödel found a solution to Einstein's field equations describing a rotating universe that contained such curves. If you lived in Gödel's universe, you could theoretically travel into your own past. However, our universe does not appear to be rotating in the way Gödel described, so this particular solution does not apply to reality. Other theoretical possibilities for backward time travel include traversable wormholes, hypothetical tunnels through space-time connecting distant points, and certain configurations involving rotating black holes, known as Kerr black holes. However, all of these proposals face severe theoretical obstacles. Many physicists believe that the laws of physics conspire to prevent backward time travel, a principle sometimes called the chronology protection conjecture, proposed by Stephen Hawking. Hawking semi-facetiously said that the universe seems to conspire to prevent time travel, as evidenced by the fact that we have not been invaded by tourists from the future. So forward time travel is real and confirmed. Backward time travel remains an open question, but most physicists are skeptical that it is possible. The arrow of time seems to point stubbornly in one direction. And speaking of the arrow of time, this is one of the deepest mysteries in all of physics. Why does time have a direction? Why do we remember the past but not the future? Why do eggs break but never spontaneously unbreak? Why does entropy always increase? The fundamental equations of physics, including Einstein's equations of general relativity, are time reversible. They work equally well forwards and backwards. If you film a perfectly elastic collision between two billiard balls and play it backwards, the reversed version is also a perfectly valid solution of Newton's laws. There is nothing in the fundamental equations that distinguishes the forward direction of time from the backward direction. And yet, macroscopically, time very clearly has a direction. We age, stars burn out, galaxies disperse. The universe evolves from a state of low entropy, high order, to a state of high entropy, high disorder. This directionality is encapsulated in the second law of thermodynamics, which states that the entropy of an isolated system never decreases. Entropy always increases or stays the same, and this law gives time its arrow. The past is the direction of lower entropy. The future is the direction of higher entropy. We remember the past because our brains store memories, which is a low entropy process, that is consistent with the overall increase of entropy. We cannot remember the future because that would require a decrease in entropy. But the second law raises its own question. Why was the entropy of the early universe so low? Why did the universe start in such an incredibly ordered state right after the Big Bang? This is the past hypothesis, as philosopher David Albert has called it, and it is one of the deepest unsolved problems in the foundations of physics. The low entropy of the early universe is the reason time has an arrow. But why the early universe had low entropy in the first place is not something we currently understand. I find it remarkable that our discussion of moving clocks running slower has led us to the very edge of what physics can currently explain. From a simple question about the rate of ticking clocks, we have arrived at the mystery of why time flows at all. This is the beauty of physics. Pull on any thread and you unravel the entire tapestry. Every question leads to deeper questions. Every answer opens new doors. Let me now bring things back to the practical and explore what time dilation means for the future of humanity, particularly for space travel and interstellar exploration. If and when humanity develops the technology to travel at a significant fraction of the speed of light, time dilation will be one of the most important practical considerations. It will shape mission design, communication protocols, and the very social structure of an interstellar civilization. Consider a relatively modest scenario. A spaceship traveling to Proxima Centauri, the nearest star system, at 10% of the speed of light. The trip would take about 43 years from Earth's perspective. At 10% of c, time dilation is negligible, so the crew would also experience about 43 years. This is a generation ship scenario, where the people who arrive are the children or grandchildren of the people who departed. There is no significant time dilation advantage. But now, consider a more ambitious scenario. A spaceship capable of sustained acceleration at 1g, the comfortable, Earth-like gravity we experience every day. If this ship accelerates at 1g for the first half of the trip and decelerates at 1g for the second half, the results are spectacular. To reach Proxima Centauri at 4.3 light-years, the trip would take about 3.6 years ship time, while about 5.9 years pass on Earth. Not a huge difference, but the longer the trip, the more dramatic the time dilation becomes. To reach Vega, about 25 light-years away, the trip takes about 6.6 years ship time, while 26.8 years pass on Earth. To reach the center of the galaxy, 26,000 light-years away, the trip takes about 20 years ship time, while about 26,000 years pass on Earth. To reach the Andromeda galaxy at 2.5 million light-years, the trip takes about 28 years ship time, while 2.5 million years pass on Earth. These numbers are staggering. A single human being in a single lifetime could in principle visit the center of the galaxy or even another galaxy. But the price is total temporal disconnection from the rest of humanity. You cannot have a conversation with home. By the time you arrive, home is unrecognizably different. Everyone you knew is dead. Your civilization may have transformed or collapsed or ascended to unimaginable heights. This creates a fascinating scenario for interstellar colonization. Imagine humanity sends out colonization ships to multiple star systems. The colonists experience relatively short travel times due to time dilation, but by the time they arrive, decades or centuries have passed on Earth. The colonies develop independently. Communication is limited to speed of light transmissions, which take years or decades to arrive. Each colony evolves its own culture, technology, language, even biology. An interstellar civilization would not be a single unified civilization. It would be a collection of loosely connected worlds, separated not just by space but by time. The colony sent out today might arrive in what, for them, is 10 years, but by the time their first report reaches Earth, 50 years have passed on Earth. Humanity on Earth might have sent out a faster ship in the meantime, using technology developed after the first ship left that arrives before the first ship does. This is the relativistic leapfrog, a genuine strategic consideration for interstellar mission planning. Now, there is a question that sometimes comes up, and it is a good one. Could we use time dilation for practical purposes beyond space travel? Could we, for example, use it for medical applications? What if a person were terminally ill and no cure currently existed, but a cure might be developed in 50 years? Could we put that person on a high-speed spaceship, have them experience a few years while 50 years pass on Earth, and then bring them back to be cured? In principle, yes. This is physically possible. Time dilation provides a real mechanism for a person to skip ahead in time. They would not be in suspended animation. They would be awake, living, experiencing time normally on the ship. But when they returned, decades would have passed on Earth, and hopefully the cure would be available. Of course, the energy required to accelerate a spaceship to relativistic speeds is currently far, far beyond our capabilities. But the physics allows it. The limitation is engineering, not physics. There are also implications for information storage. A time capsule placed in a strong gravitational field or sent on a high-speed journey would age more slowly than its surroundings. You could preserve information not just in physical durability, but in temporal displacement. Send a hard drive on a near-light-speed trip, and while millennia pass for the rest of the universe, the hard drive experiences only years of wear and tear. These applications may sound fantastical, and they are certainly beyond our current technology, but the underlying physics is real and confirmed. Time dilation is not a theoretical curiosity. It is a feature of the universe that we could, in principle, exploit. We are limited only by our engineering, not by the laws of physics. Now let me address some common misconceptions about time dilation, because there are many, and they can be a source of real confusion. The first and most common misconception is that time dilation only affects clocks. People sometimes think that the clocks slow down because of some mechanical effect of motion, that the gears are stressed, or the electronics are disrupted, or something physical happens to the clock mechanism. This is completely wrong. Time dilation affects everything. Every physical process without exception slows down. Chemical reactions slow down. Biological processes slow down. Radioactive decay slows down. The firing of neurons slows down. Aging slows down. It is not that clocks run slow while everything else continues normally. Everything runs slow. Time itself passes more slowly. The reason it is called time dilation rather than clock dilation is precisely this. It is time that is dilated, stretched, slowed. If only clocks were affected, it would be a mundane mechanical problem. But it is time itself, the universal stage on which all events play out, that runs at a different rate. The second common misconception is that you would feel time passing slowly. People imagine that traveling at near light speed would feel like moving through molasses, like everything is in slow motion. This is wrong. From your own perspective, everything is completely normal. Your clocks tick normally, your heart beats normally, your thoughts flow at their usual pace. You do not feel any slowing. You cannot detect time dilation by looking at your own clock. Time dilation is something that is observed only when comparing clocks in different reference frames. If you could somehow look out your spaceship window and see a stationary clock, you would see that clock ticking faster than yours. But your own experience is completely, utterly normal. This is one of the most counterintuitive aspects of time dilation. It is invisible from the inside. You can never catch it in the act by examining your own frame of reference. You need to compare with another frame to see the effect. This is why we lived for thousands of years without noticing it. We had no way to compare clocks in sufficiently different reference frames with sufficient precision. The third misconception is about the speed of light limit. People often express this as nothing can go faster than the speed of light, and then immediately think of counterexamples. What about the expansion of the universe? What about quantum entanglement? What about shadows or laser pointers swept across the surface of the moon? The correct statement is that no information, no causal influence, can travel faster than light through space. The expansion of space itself is not bound by this limit. Distant galaxies can recede from us faster than light, because it is space itself that is expanding, not objects moving through space. But we cannot send a signal to those galaxies faster than light. We cannot use the expansion of space to communicate. Quantum entanglement does involve correlations between distant particles that seem to be instantaneous, but careful analysis shows that no information is actually transmitted. You cannot use entanglement to send a message faster than light. The correlations are real, but they cannot be exploited for communication. And things like shadows and laser-pointed dots can indeed move across a surface faster than light, but no information or energy is actually traveling at that speed. The dot of a laser pointer on the moon could sweep across the surface faster than light if you wiggle the laser fast enough. But no physical thing is actually moving at that speed. Each photon in the beam is still traveling at c. So the speed of light limit is about information and causality, not about every conceivable velocity-like quantity. This is an important distinction, and it preserves the self-consistency of relativity. The fourth misconception is the idea that relativity has been disproven or is somehow controversial. This is completely false. General relativity and special relativity are among the most thoroughly tested theories in the history of science. Every test, every experiment, every observation, from the perihelion precession of Mercury to the bending of starlight by the sun to the detection of gravitational waves by LIGO, to the image of a black hole by the Event Horizon Telescope, to the daily operation of GPS, confirms relativity. There is not a single confirmed observation that contradicts it. The theory is not perfect, it breaks down at singularities and cannot be reconciled with quantum mechanics in certain extreme regimes. But within its domain of applicability, It is astonishingly, spectacularly accurate. If someone tells you that Einstein was wrong or that relativity has been disproven, they are wrong. The evidence is overwhelming, and the very technology you are using to watch this video, from the GPS in your phone to the atomic clocks in telecommunications networks, relies on relativity being correct. Now let me zoom out even further and place time dilation in a cosmological context. We have talked about clocks on airplanes and satellites and spaceships. But time dilation operates on the scale of the entire universe. When we look at distant galaxies, we are looking back in time because the light from those galaxies takes time to reach us. But we are also looking at a universe that is expanding. The expansion of the universe stretches the wavelength of the light from distant objects, making it redder. This is cosmological redshift, but there is also a time dilation effect. Events in distant galaxies appear to be slowed down from our perspective. This was dramatically confirmed in 1995 and subsequent years with observations of Type 1a supernova, stellar explosions that serve as standard candles for measuring cosmic distances. When astronomers observed supernovae in distant galaxies, they found that the light curves, the way the supernovae brightened and faded, were stretched in time. A supernova that brightens and fades over a few weeks in a nearby galaxy takes longer to brighten and fade in a distant galaxy. The time stretch is exactly proportional to 1 plus the redshift, which is exactly what cosmological time dilation predicts. This was one of the key observations that led to the discovery of the accelerating expansion of the universe and dark energy, which won the Nobel Prize in Physics in 2011. So time dilation is not just a local phenomenon. It is a cosmological phenomenon. We can see its effect across billions of light years. The entire observable universe is a laboratory for testing relativity, and every observation confirms the theory. Now let us go even further back in time to the very beginning, to the Big Bang itself. In the first moments of the universe, conditions were so extreme, temperatures so high, densities so great, that the known laws of physics, including general relativity, may break down. At the Planck scale, where times are on the order of 5.39 times 10 to the minus 44 seconds, the so-called Planck time, and distances are on the order of 1.6 times 10 to the minus 35 meters. The Planck length quantum gravitational effects become important, and we do not yet have a theory that can handle them. The Planck time is the smallest meaningful unit of time in our current understanding of physics. Before the Planck time after the Big Bang, we simply do not know what happened. We do not even know if the concept of time, as we understand it, applied. Some physicists have speculated that time itself may have emerged from the Big Bang, that there was no before the Big Bang because time did not exist before it. Asking what happened before the Big Bang may be like asking what is north of the North Pole. The question is grammatically valid, but physically meaningless. Time, like space, may be a feature of the universe that came into existence with the Big Bang, not a pre-existing stage on which the Big Bang occurred. This is one of the deepest and most difficult questions in all of physics and philosophy. What is the origin of time? Did time begin? Could time end? These questions are at the frontier of human knowledge, and they remain unanswered. And speaking of the end, what happens to time at the end of the universe? Current observations suggest that the universe will continue expanding, possibly forever. and that this expansion is accelerating due to dark energy? In the far, far future, the universe will undergo what is sometimes called the heat death. Stars will burn out. Galaxies will drift apart. Black holes will evaporate through Hawking radiation, a process that takes unimaginable spans of time, perhaps 10 to the power of 100 years. Eventually, all the energy in the universe will be spread out into a thin, cold, uniform soup of low-energy particles and radiation. Nothing will happen. Nothing will change. The universe will be in a state of maximum entropy. In such a universe, does time still exist? If nothing changes, if no events occur, if there are no processes to measure, does time still flow? This is a question that has troubled physicists and philosophers alike. Some argue that time is defined by change, and in a universe with no change, time ceases to have meaning. Others argue that time could still exist as a mathematical dimension, even in the absence of events to mark its passage. We do not know the answer, but it is a beautiful question, born from the same investigation into the nature of time that started with moving clocks running slower. Let me take you now to the human side of this story. Behind all the equations and experiments and cosmic implications, there is a human being, a man who changed our understanding of the universe more profoundly than anyone since Newton, and arguably more than Newton himself. Albert Einstein. Einstein was born in 1879 in Ulm, Germany. Contrary to popular myth, he was not a bad student. He excelled at math and physics from a young age, but he was rebellious, questioning authority, challenging his teachers, refusing to accept ideas simply because he was told they were true. He applied to the Swiss Federal Polytechnic in Zurich and was admitted, though he had to complete an additional year of secondary schooling first. He graduated in 1900, but could not find an academic position, so he took a job at the Swiss Patent Office in Bern, examining patent applications. It was during his time at the Patent Office, working in relative obscurity, that Einstein did his most revolutionary work. In 1905, his miracle year, he published 4 papers that each would have been career-defining on its own. The paper on the photoelectric effect showed that light comes in discrete packets called quanta, and it would eventually win him the Nobel Prize. The paper on Brownian motion provided strong evidence for the existence of atoms. The paper on special relativity introduced the theory we have been discussing, demolishing absolute time and establishing the relativity of simultaneity, time dilation, and length contraction. And the paper on mass-energy equivalence gave us the most famous equation in physics, E equals mc squared. 4 papers, 1 year, all while working full-time at a patent office. It is one of the most extraordinary intellectual achievements in human history. But Einstein was not done. Special relativity dealt with constant speed motion. Gravity was missing from the picture, and Einstein knew it. From 1907 to 1915, he worked obsessively on extending his theory to include gravity. This was enormously difficult. The mathematics required, tensor calculus and Riemannian geometry, was far beyond what Einstein knew at the time. He had to learn it, often with the help of his mathematician friend Marcel Grossmann. He made wrong turns. He published incorrect equations. He despaired. And then, in November 1915, after years of struggle, he found the correct equations, the Einstein field equations of general relativity. The equations that describe how mass and energy curve spacetime. The equations that predict black holes, gravitational waves, the expansion of the universe, and all the gravitational time dilation we have been discussing. The first major confirmation of general relativity came in 1919, when a total solar eclipse provided the opportunity to test one of the theory's key predictions: that light from distant stars would be bent by the sun's gravitational field. 2 expeditions were mounted, one to Principe off the west coast of Africa, and one to Sobral in Brazil, to photograph stars near the edge of the sun during the eclipse and compare their apparent positions to their known positions when the sun was not nearby. The results confirmed Einstein's prediction. Starlight was bent by the sun by the amount predicted by general relativity, which was twice the amount predicted by Newtonian gravity. The announcement of this result made Einstein a global celebrity. Overnight, the Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Einstein became the most famous scientist in the world, a position he held for the rest of his life and arguably still holds today. But Einstein's story also has a bittersweet coda. He spent the last 30 years of his life, from the mid-1920s until his death in 1955, searching for a unified field theory, a single theoretical framework that would encompass both gravity and electromagnetism, and perhaps eventually quantum mechanics as well. He never found it. The problem was too hard. The mathematics was too difficult, and Einstein became increasingly isolated from the mainstream of physics, which had moved on to quantum mechanics, a theory that Einstein deeply mistrusted. Today, the search for a theory that unifies general relativity and quantum mechanics, a theory of quantum gravity, is the single biggest unsolved problem in fundamental physics. String theory, loop quantum gravity, causal set theory, these are all attempts to find the unified theory that Einstein dreamed of. None has yet succeeded. The next Einstein, whoever they turn out to be, will be the person who cracks this problem. And when they do, our understanding of time, of space-time, of the very nature of reality will undergo another revolution. Now let me share some final astonishing facts about time dilation that I think will stay with you long after this video is over. Fact 1. Your feet age slower than your head. We mentioned this earlier, but it bears repeating. Because your feet are closer to the center of the Earth in a slightly stronger gravitational field, time passes slightly slower at your feet than at your head. Over a typical human lifetime, the difference accumulates to about 90 billionths of a second. This is tiny, but it is real. It has been measured. Your body is a time dilation experiment. Fact 2. The core of the Earth is about 2.5 years younger than the surface. Over 4.5 billion years, gravitational time dilation between the core and the surface of the Earth has accumulated to about 2.5 years. The center of our planet has experienced 2.5 fewer years than the surface. It is younger. This is not a metaphor. This is a physical fact. Fact 3. If you could orbit a black hole at just the right distance, you could experience 1 year while 100 years, or 1,000 years, or 1,000,000 years pass in the rest of the universe. The time dilation factor near a black hole can be made arbitrarily large. Black holes are the most extreme time machines the universe offers. Fact 4. Time dilation means that there is no such thing as a universal simultaneous now across the universe. The phrase "at this very moment" has no objective meaning. when applied to distant locations. The present is local, not global. Fact 5. At the speed of light, time stops completely. A photon, a particle of light, experiences no passage of time. From a photon's perspective, if such a perspective can be defined, its creation and its destruction are the same event. A photon emitted from a star billions of light years away, one that has been traveling through the cosmos for billions of our years, has experienced zero time. Not a little time. Zero time. The journey from the most distant reaches of the observable universe to your eye takes, from the photon's perspective, no time at all. I want you to sit with that for a moment. The light that lets you see, the light that brings you warmth, the light from the sun that sustains all life on Earth. The photons of that light have experienced no time. They are emitted and absorbed at the same instant, by their own reckoning. Every photon that has ever existed in the history of the universe has experienced no time. They exist in a kind of eternal present. The universe, from the perspective of light, is instantaneous. Now let me draw all of these threads together and bring this journey to its conclusion. We started with a simple question: why do moving clocks run slower? And the answer we have found is far deeper, far more profound, far more transformative than we could have imagined. Moving clocks run slower because time is not what Newton thought it was. Time is not a universal river flowing at the same rate for everyone. Time is a dimension of space-time, and space-time is dynamic, responsive, flexible. The speed of light, that universal constant, that number embedded in the very equations of electromagnetism, forces time to behave this way. If the speed of light is the same for all observers, then time must be different for different observers. It is not optional. It is not a choice. It is a logical, mathematical, physical necessity. The light clock thought experiment shows us this with crystalline clarity. A clock moving through space has its light traveling a longer path, but the speed of light cannot change, so the tick takes longer. Time dilates, not the clock's time. Time itself. Every process, every atom, every heartbeat, every thought slows down in the moving frame as seen from the stationary frame. And the effect is symmetric. Each observer sees the other's time running slow. The paradox dissolves when we recognize that the symmetry is broken by acceleration, as the twin paradox resolution shows. The experiments confirm everything. Hafele and Keating proved it with atomic clocks on airplanes. Muon decay proves it every time cosmic rays hit the atmosphere. Particle accelerators prove it in every collision. GPS proves it every time you ask your phone for directions. NIST atomic clocks prove it over a height difference of 33 centimeters. The evidence is not ambiguous. It is not uncertain. It is as solid as anything in science. General relativity extends the picture from speed to gravity. Massive objects curve space-time, and time runs slower in stronger gravitational fields. The surface of a neutron star, the vicinity of a black hole, even the difference between the top and bottom of a tower, all show this effect. Both types of time dilation, velocity-based and gravitational, are aspects of the same underlying geometry of space-time. The philosophical implications are staggering. There is no universal now. The past, present, and future may all be equally real in a timeless block of space-time. Forward time travel is real and experimentally confirmed. The arrow of time, the reason we remember the past but not the future, is tied to the low entropy of the early universe, which remains one of the deepest unsolved puzzles in physics. And the practical implications are everywhere. GPS, particle physics, satellite communications, future space travel, all depend on the reality of time dilation. It is not an esoteric theoretical curiosity. It is woven into the fabric of modern technology and the future of human civilization. So let me return to where we began. Look at the clock again. Those ticking seconds, that steady, reliable march of time. It feels absolute. It feels universal. It feels like the one thing you can count on to be the same everywhere, for everyone. But it is not. Your clock is ticking at a rate that depends on your speed and the gravitational field you're in. It is your time, personal to you, shaped by your journey through space-time. Someone else moving differently or in a different gravitational environment has a different time. And both are equally real. This is not an illusion. Let me say it one final time. This is not an illusion. It is not a trick. It is not a malfunction. It is not an error. It is the fundamental nature of reality. Time is relative. Time is flexible. Time is personal. Moving clocks run slower. Clocks in stronger gravity run slower. And the universe has confirmed this in every experiment, every observation, every measurement we have ever made. We live in Einstein's universe, a universe where space and time are woven together into a single fabric that can stretch and curve and warp. A universe where the speed of light is an absolute, unchanging constant, and everything else, time, space, mass, energy, rearranges itself to accommodate that constancy. A universe that is far stranger, far more beautiful, far more awe-inspiring than the clockwork Newtonian cosmos that our intuition would have us believe in.